So let's do a problem just looking at horizontal asymptotes. So find the horizontal asymptotes for this rational function. Now we can go back to our definition here. Actually, I should be here first. So let's look at our numerator. We have that the degree of the numerator is 3. And our denominator, we can see, has a degree of 4. So in this case, our n is less than m. And coming over here, we see that of our 4 options, really, that we are still with number 1, we saw that recently, where n is less than m. So that tells us that y equals 0 is a horizontal asymptote. So y equals 0 is our horizontal asymptote. Now I'm going to show you something that I can do. I can rewrite this to maybe show you why that is a little bit better. But if I take this function and I divide top and bottom by the highest degree in the denominator, so I divide the numerator and denominator every term by x to the 4th. That's what I'm going to do. So I'm going to have x cubed divided by x to the 4th. I'm going to have 3x squared divided by x to the 4th. And so on with every term. And then what you want to understand is to keep this rational function equivalent, I also have to then divide everything in the denominator by x to the 4th. That means that what I'll be doing is essentially just dividing this whole thing by 1, which is x to the 4th over x to the 4th. So that keeps everything at least legit, so that all I'm doing is rewriting it and not changing the function fundamentally. So now I can simplify each term. So I'm just simplifying, variables with exponents. So notice that x cubed over x to the 4th is 1 over x. If you want, you can pause and you can see if you can simplify the other terms as well. Okay. Okay, so the idea with horizontal asymptotes is to think about what happens as x goes to 0. So what I want you to see here is, as x goes to infinity. So as x goes to infinity, what I want you to see is if we look at all the pieces of this, as x goes to infinity, this piece goes to 0 because x gets very big, so that piece gets very small. This piece also goes to 0. This piece also goes to 0. It doesn't matter. Notice all my numerators here are constant. So being divided by some variable that's getting bigger and bigger means that each term is going to get smaller and smaller. Even this term is also going to go to 0. In my denominator, this value does not change. As x gets bigger and bigger, it's just 2. This term, however, goes to 0, and this term goes to 0. So the big idea that I want you to see here is that the numerator is going to 0. The denominator is going to be 2. It's going to be heading to 2 because everything else is gone. So what that means is the numerator is heading to 0, the denominator is heading to 2, 0 over 2 is 0. That's the idea here, that's what's happening. I'll try to show you another example as well of something slightly different, but using the same technique to show you like a different example. But it does mean that for this rational function, the horizontal asymptote is y equals 0. Now we have another full asymptote here, or a full rational function that we need to find things like asymptotes for and x-intercepts, y-intercepts. Our job is to graph it. That is what we're going to be asked to do here. So notice we should start by finding x-intercepts, y-intercepts. You're welcome to do that already. See what you can do, getting your x-intercept, any x-intercepts, any y-intercepts. See if there are any. My first step is typically going to be to see if I can do any type of factoring, because that helps me. So y-intercept, f of 0 is going to equal -1 over 0. Well, that is a problem because that is not a thing. So there is no y-intercept. So there is no place where we're going to touch the y-axis. Okay, so that is good to know. That's a piece of information. We like it. If you are really following along, you should realize that that already means that there's going to be a vertical asymptote there. So no y-intercept. Okay. X-intercepts would be when the numerator is equal to 0. So we do have one x-intercept, 1, 0. And then I'll come over here and I'll think about vertical asymptotes. So the denominator, I'll put the factored version here, cannot be equal to 0. So you can think about what those vertical asymptotes are going to be. X equals -2. So we have two vertical asymptotes at 0, -2, and a horizontal asymptote. I'll rewrite it here. We can see this, even though the degrees are different, they still follow that same example that we just saw. So our numerator is n equaling 1, the degree of it. The denominator is m equaling 2. So in this case, n is less than m. So that tells us that our horizontal asymptote will be y equals 0. So we kind of already knew that because there's no y-intercept because it makes the denominator 0, but okay. So I think I kind of liked the orange. Let's see. So I'm going to put my asymptote at 0, vertical asymptote at 0. I'll put my vertical asymptote at -2. I'll put my horizontal asymptote at y equals 0. So remember, I'm going to be careful not to touch those vertical asymptotes. And then I can put on, if I'd like, we do have one x-intercept at 1, 0. So do know that you can touch and cross a horizontal asymptote. You cannot touch a vertical asymptote, but you can touch a horizontal asymptote. The horizontal asymptote, the idea is what happens is x gets very big positively as x gets very big negatively, but you can still touch it. And we're going to be crossing it right now. Like, it's okay to cross it. However, long term, we're going to be approaching 0, our function will be. Okay, so I think everything I have so far on here. And now I just need to think about these values. So now I can make my sign chart. And I have my, I want to put in all of my asymptotes here, my vertical asymptotes, I should say. Vertical asymptote, and x-intercept. There we go. And now I just need to see what's happening on either side. I know what's happening to y here as x goes out to infinity, -infinity. And we just do the same. We're just going to test some points here. So we're going to test x equals -10. So look in your function here. If we plug in -10 to our function, all I care about is the signs. I'll have in my numerator a negative, and in my denominator a negative times a negative. So negative, negative, negative is going to give me negative. So our function will be below the x-axis all the way up to -2, approaching those asymptotes. Between -2 and 0, I'll go with a -1. If I plug in -1, I'll have a negative over a negative times a positive. Yep, that's it. So that's going to give me a positive because a negative divided by a negative is a positive. So I'll be above the x-axis between -2, 0. Then we'll choose something like a half. And in my numerator, I will have a negative. My denominator, positive times a positive. So negative divided by a positive is a negative. So I'll be back underneath the x-axis. And then x equals, let's get crazy, 15. So if I plug that in, so these are just my test points here. If I plug in something like 15, I'll have positive, 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 and be positive. There we go. So we're going to be above the x-axis, below the x-axis, above, below, above. So let's take a look. So notice we have essentially 4 things to be thinking about here. Up until -2. So we have something that's happening up until here. Then we have something that's happening between here and here. Then we have something that's happening between here and here. And then we have something that's happening after that. So those are our like little 4 intervals here. So up until -2, we said we were negative. So we need to be underneath the x-axis, approaching those asymptotes. There we go. That's the only way this can look. It's got to approach both of those asymptotes. There we are. We said that between -2 and 0, we were positive. Remember, we cannot touch the x-axis. There is no intercept. So we have to just have positive values, but we also have to approach those vertical asymptotes. So, you know, it does something like this. If you want to be, you know, have a slightly more specific graph, you can, if you want, you know, put in a value like -1, see what comes out, and you could get a y value that would just kind of tell you where you are at -1. Now, after 0, but before 1, we are negative. So we need to be underneath the x-axis, and we need to be coming up to 0 to the 0.10. And then after that, we are positive, but again, long term, we have to approach that other horizontal asymptote. So I'm going to come up, but then as I keep going, I'm going to get close again to that horizontal asymptote. So here's a sketch of what this function looks like, and that's using all the pieces that we've talked about to get an idea, and looks pretty good. All right, so got a little lit up on the last video there due to the afternoon sun. So we are back in the morning, doing a little bit more here, hopefully not distracting you with bars of light. We're going to take a look at an example of a rational function that we're going to graph, but it's going to have what's called an oblique asymptote. That's also sometimes known as a slant asymptote, and that's literally because it's an asymptote that slants. So instead of being vertical or horizontal, it's an asymptote that is slanted. It is a special situation, and I'll get there, but just give me a little bit of time and I'll show you where it comes in. First off, we're still graphing a rational function here, so we're just going to find the typical values f of 0. Notice that this one's very similar to what we've done before, but flipped, so that does change it. So if we plug in 0, we actually get 0 over -1, which is 0. So we're going to have a y-intercept of 0, 0 on this one. X-intercepts, remember, that is when the function is equal to 0. And for a rational function, that is when the numerator is equal to 0, because that's the only way that it can be equal to 0. So we get x squared plus 2x, when is that equal to 0? And then we just factor. And you can see that we get x equals 0, -2. We already knew 0 was going to be there because of the y-intercept, but now we have another x-intercept as well. In terms of vertical asymptotes, it's probably pretty easy to see. The denominator cannot equal 0, and so that means that x cannot equal -1. So x equaling -1 is the vertical asymptote. Okay, so now comes the exciting part, kind of. All right, so thinking about the horizontal asymptotes here, what I want you to notice is that we have a special situation where the numerator has a higher degree than the denominator. So the numerator has a degree of 2, the denominator has a degree of 1. Specifically, I'm going to take us back here. We are now in situation 3, which we have not seen. And what situation 3 is saying when the numerator has one higher degree than the denominator. So when n equals n plus 1. But again, all that means is the numerator is of a higher degree than the denominator by 1. What happens is we end up with an oblique asymptote or a slant asymptote, which is a line. You know, we can imagine that if we have something like this, that this is a straight line. However, it's going to have a slope, y-intercept, things like that. Now, it is found using division, which we did recently. We've done division. So we find it by doing literally the top divided by the numerator divided by the denominator. Okay, so here it is. So again, what I was saying was n is 2, the degree of the numerator, the degree of the denominator is 1, and so n equals m plus 1. One more, so that's, you know, situation number 3. So when we have f of x equaling x squared plus 2x over x plus 1, to find this oblique asymptote, it is literally taking x squared plus 2x and dividing it by x minus 1. That is what it means to do division. You're actually doing the division there. Now, what we can do, however, is we can do this using synthetic division. So we could do this if you want, if you're comfortable with that, you can do that. You can also recognize that because we're dividing by x minus 1, that we could use synthetic division instead. So we have 1, and we have 2, and we have no constant, so I'm going to put a 0 there because the constant is 0. And we just, like I said, we use synthetic division, see what we get. You're welcome to pause if you want. You know how to do synthetic division now. Okay, so what this means to get this is that when you do this division, you are going to get, so it's a square, x squared divided by x, so you get x plus 3, and then you have a remainder of 3, so remainder of 3. But I want you to understand that the remainder doesn't matter, it doesn't have anything to do with your asymptote. The asymptote is now the line y equals x plus 3. Yes, I know, okay? So that is the oblique asymptote. So I'll go ahead and put that on our graph, why not here? So understand y equals x plus 3. It is a line that has y-intercept 0, 3. You should also recognize that it has slope of 1 over 1, slope of 1. So you can put on the point, y-intercept there, and then just some of the slope points. Again, that's just 1 over 1. And then, you know, not surprisingly, the big thing to understand here is it's an asymptote that our function is going to approach. So I'm just going to, just like I've done with my other asymptotes, I'm just going to draw this lovely dotted line here because I'm going to get close to this as x gets really big in either direction, but it is still an asymptote. Okay, so I'm just going to leave that there. Let's see. I'm sure we can put some other points on here. Let's see. What else have we got? We've got 0, 0, and negative 2, 0. Let's go ahead and put those on our graph. 0, 0, negative 2, 0. Got those. We also have a vertical asymptote at 1. So we can go ahead and add that in there. Okay. Dun, dun, dun. Okay, remember we cannot touch a vertical asymptote. Our graph should not touch that vertical asymptote. And now we're ready to do our sign chart. Sign chart. So I'm still going to think about negative infinity to infinity, but in this case, we are not approaching a horizontal asymptote, we're approaching this line. So although it might sound weird, we are approaching the line x plus 3 because our graph is going to get near that line, that oblique asymptote that we just created. So we can write that. We need to add in our intercepts and our vertical asymptote. So in, numerical order here. So we've got that. Remember, this is a vertical asymptote, so we're not going to touch that. These are intercepts. And then we just do the sign chart. You can, if you want, this can be helpful so that you can really just see positive or negative. Are we above the axis? Are we below? I would recommend pausing, seeing if you can come up with the values, the positive or negative that goes in between. Be a good time to do that. And then come back and see if you got it right. So we pick something between negative infinity, -2. That's going to be, negative 20. If I put negative 20 into my original, my factored form here, I'm going to have negative, negative, negative. That's 3 negatives, so I'm going to keep that negative. I'll pick -1 in between -2, 0. If I put in -1, that's going to be negative, positive, negative. So that's going to be a negative divided by a negative or a positive. I have to pick like a fraction between 0 and 1. So maybe I'll pick a half and I'll get positive, positive, negative. It's going to give me a negative. And then from 1 to infinity, I will pick positive 20. And that's going to give me positive, 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 and I am positive. So we're going to switch from negative to positive on all sides of our asymptotes and intercepts. So let's see what happens here. So we're starting off by being from -2 up to, or negative infinity up to -2, we are negative. But we do have to reach this intercept here. So it's going to make sense that our function is going to get close to this oblique asymptote all the way up to -2. Then, looking at your sign chart, we're positive from -2 to 0. Well, that makes sense. We're just going to come up and we're going to come back down. Then, as you can see, from 0 to 1, we are negative. All our y values need to be negative. And of course, it makes sense that we're approaching this vertical asymptote, which we need to do. Now, for the last piece, which is, greater than 1, we are positive. And you might be like, okay, where does that go? Please do not write this yet. Some students might think, okay, I've got to approach my asymptotes. Maybe I'm here like this. Maybe I'm here like this. There's a couple issues with that. Number one, that sends you into negative y values. You know that your y values should be positive, so you should not be down here. You should not be down here. It's not possible. You should have positive y values. You also don't have another x-intercept, so you shouldn't even be crossing the x-axis. So that's telling you that that is not correct, that you should not be down there. There we go. But you're right in thinking, if you're thinking, well, we do have to approach the asymptotes, we do. So here we have this vertical asymptote. We're going to come down, and then we just kind of scoop along, and then we head towards the other asymptote, our oblique asymptote, and it looks something like this. And that space where I switch around is just a sketch here. We're doing the best we can with our graph, but we don't know exactly where it stops unless we pick some x values and plug them in. But you can see that this function is, besides x equaling 1, we have a pretty open domain here. Every other value is possible. It's just going to head up, 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 up. I should come this way, up, 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 up. And then it goes down to that asymptote. And then over here, it's coming down and then heading out, 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 out. But it is following that line. So that's the idea of that asymptote, is instead of getting close to a horizontal asymptote, which happens in our other situations, we're getting close to that line. And that's an example of something with an oblique asymptote.